what I've promised, layer resolved electronic structure in oxide heterostructures. I'll define what I mean by them, but let me start by acknowledging what made these studies possible, in particular in funding. It's an animation of India, Department of Science and Technology. Swedish Foundation contributed significantly in the early parts, and more recently, Jamshedji Tata Trust. And what is important, of course, well, I'll be introducing the people who are involved in the talks in the various parts, because there are 2 or 3 separate parts. The plan of the talk is that I'll first very briefly point out what the difficulties are. Then I'll talk about the technique that we employ so that you have an appreciation of how we get the data or the conclusions that I'll be talking about. Then I'll apply that technique into 2 very important and very famous system, one that we abbreviate as LO-STO. LO stands for lanthanum aluminate, and STO stands for strontium titanate, and then strontium titanate and lanthanum titanate heterostructure. Let's get started with the difficulties. Difficulties really is because I'm going to talk about heterostructure, and a heterostructure is necessarily defined by having an interface, because it's 2 different materials. So there's a plane which has no perpendicular dimension. It's only an XY plane. On one side, you have material A. On the other side, you have material B. And these 2 materials together define what the interface is. And the difficulty in studying such an interface is the fact that, by definition, as I just now explained, an interface is typically buried under a depth, right? It has no width, but it is buried below a certain volume, because you have 2 different things on 2 different sides. So you need to look inside, and the part that you want to look at has no width at all in that direction when you're looking in, which means that it's extremely thin, because if it would be very thick, then you have a phase there, and it's not the interface that you're looking at. So it's hidden from you, and being very thin, any volume averaging technique will not give you the signal, because the signal sensitivity would be very small, because you'll see everything on both sides, A and B. The interface of A and B contribute very little. So what you really need is a technique that is a microscopic technique, obviously. And often this talk, I term it as doing microscopy without a microscope. And I'll explain why. So because you need a spatial resolution. So you need a microscopic technique that has the ability of penetrating through some material to reach to the interface, and then be very sensitive to that thin layer, which you can call an interface, and not be sensitive. So you need that spatial resolution in that direction if you're looking down towards the interface. How to do that is what is the question. And also I've pointed out non-invasive, because very often, and I'll show you an example of it, we can look at the interface of AB material by doing cross-sectional TM. There was some example of that in several talks earlier, and I think Milonstock as well as Bhupenstock had them. What you do in that case, you have an A and B, 2 materials, one on top of the other, and then you cut it here, and then you look from this side, so that you can see the interface as a line. The problem is that, first of all, you're seeing the interface as a line, but what is worse is that in order to get to that interface, you introduce a new interface of this material with the vacuum, because you cut it. So there's no way of looking at that interface by STM or cross-sectional TM without introducing a new interface, which is the interface of the material with the vacuum. And that, in principle, can change the properties. So you want to do something where this cutting, breaking, etc. will not be involved. And that's what I imply by calling it non-invasive. And you need the contrast that I have already told, because the interface, the perpendicular to it. So the contrast, so if you're looking down, the interface is defined by something is up here and something else is down there. So it is in this direction, it's homogeneous. So if you have a spatial resolution like in a microscopy, which is normally in the lateral direction, you'll not see any changes. And that's why you have to come from cross-sectional TM from the side, because the contrast happens to be in the perpendicular direction. So how to do that, and the proposal that we made, that it can be done with photoemission spectroscopy. Obviously, it's a bit of a misnomer, because spectroscopy is, in principle, is not a microscopic technique, but I'll point out how we end up using it. It comes from the fact that you have a tunability of surface sensitivity, and let me define what I mean by that. So that brings me to the technique employed. It's actually a very old technique. It's not that we introduced it. We've been using it for a very long time in various guises. In fact, Professor Kalabaran-Maiti extensively used it way back in 98 in this paper, using laboratory sources to understand how electronic structure of a given bulk material without any heterostructure can be different near the surface compared to what is in the bulk. So basically, the surface itself defined as sort of an interface. But with the advent of very modern synchrotron sources, things have become much better, and we have been looking at many nanomaterials. These were bulk materials that we looked at. These are nanomaterials because the tunability that I'm talking about gives us an extra dimension to play with. The way we do that, and we can do that, all of you know what photoelectron spectroscopy is all about. Photoelectron spectroscopy is a very simple technique where it's just the photoelectric effect. So you bring in a photon, a monoenergetic photon. You know the energy of the photon. It interacts with an electron. The electron absorbs the photon completely and gets excited. If the energy of that photon was large enough, then you overcome the binding energy of the electron in the material, so it comes out into the vacuum. It comes out in the vacuum with the kinetic energy, which is, of course, given by the energy conservation principle, which means the kinetic energy is equal to the photon energy that you give and the binding energy that you need to overcome, and that's the equation that's given over here. So the kinetic energy of the electron that's coming out is given by the photon energy, which you know, and the binding energy of particular core level of the element that you are trying to understand. Now, the binding energy is, of course, fixed. That's the property of the element and its oxidation state and chemical environment. So it's very characteristic of the material. You can find out what element is there and in what oxidation state, and that's fixed. But you can vary the photon energy. When you vary the photon energy, what you are doing, you are varying the electron kinetic energy. Now, I told you that the photoemission process is the absorption of a photon and the electron coming out with a certain kinetic energy, and you detect this electron out in the vacuum. But the electron in the first step gets produced somewhere deep inside the material, right? Because the photon penetrates into the material, it gets excited, the electron gets excited somewhere inside, and then the electron has to travel through the material and then come out. Once it comes out, it's all very nice and fine, but before it comes out, in the process of its traversing through the thickness of the material, this electron can, of course, suffer inelastic processes by scattering with other things, other atoms, electrons, defects, what have you. If it does scatter that way, then this inelastic process will steal energy out of it so that this energy conservation that I use will be no more valid, and that electron will be lost from the photoelectron signal. So basically, the photoelectron signal is the one which does not scatter inelastically. So it's very important to know what is the probability that this electron will come out of the material without suffering an inelastic process, and that we characterize by a typical length scale, which is the average length or distance that an electron can travel inside a material, in a given material, without being scattered inelastically. So that is the average approximate thickness that I can probe with photoemission, right? So I come in with photons. Photons can go deep inside. It doesn't matter. The electrons only from lambda thickness, which is my inelastic mean free path, is if it is generated within that much of the surface, and if it has the right orientation, it will come out of the surface, and I can measure that. And that's a quantity which we call the escape depth is plotted over here. It happens to be a very sensitive function of the electron kinetic energy. And it has this particular shape that it, from small photon or kinetic energies, it starts with a large value, goes down and comes up, and then again becomes large. You may think it's a bit peculiar, but it's very easy to understand why it should happen, because you can imagine the limiting value of zero kinetic energy. If the electron that I ejected has zero kinetic energy, it cannot suffer any inelastic loss because it has no energy to give. So it will have an infinitely long escape path. Similarly, if the electron has infinite, very high energy, it has a lot of energy to give, but it will zip past everything so fast that it will not interact with the material. And again, it will have a very large mean free path or escape depth. That's why in the both ends, at very low energy as well as very high energy, it must be very high. So it has no other option but to have a minimum somewhere in the middle. But what is important is the fact that this minimum happens to be around 100 electron volt kinetic energy. And even more important is to notice that minimum is in the order of some 5 or 6 angstrom, which means that the photoemission signal that you're getting is in the order of typically 2 or 3 times the escape depth, because it's not a step function but an exponentially decaying function, the probability of coming out. So you are going to see only the top 5, 10, 15 angstrom if you chose the photon energy there, the electron kinetic energy there. Now what we can do, of course, by choosing the photon energy, I can make the electron kinetic energy at any point that I want, and if I ignore the low energy, that means for the same binding energy, same element, by changing the photon energy, I can put the electron energy there, 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 or there, and therefore get different depth into the system. So I can look inside the system stepwise by changing the photon energy. And to schematically motivate you, if you have a homogeneous alloy system, which is given by one single color, may have multiple components, and the same components distributed, but with a changing composition, and if I want to figure out what is what I can do is to come with a photon, which will be very low energy photon, so my escape depth is very small, and so I'll be seeing only the top part, because that's a slice, that's my mean escape depth. And I'll see what the composition is. But I want to map out the entire composition. So what I'll do is to stepwise increase my photon energy, and I'll go to that step. And the differential between these two steps that I showed, if the escape depth controls in a rectangular fashion rather than the exponential fashion, then between this previous step and this step, if I take the difference of the spectrum, then I get exact composition within that slice. And since the photon energy, and I can go on doing this as much as I want. And since the photon energy can be changed by any small arbitrary amount, I can make these slices as thin as I want in principle and exquisitely map out exactly how the composition varies. Not only how the composition varies, I can also map out how the electronic structure varies. By that I mean, I can look at the electron distribution near the Fermi energy, which controls its physical and chemical properties, and directly map out how the electronic structure varies as a function of depth. This is a technique that we have used extensively. I'll not go into that, but what is more important is to ask the question, yes, in principle that happens, but do we actually see changes in the spectrum when I change the photon energy? Do we really have a sensitivity to talk about such that I would have, because this principle would work, but if it is not sensitive, the error bar would be very large. To motivate that, I'll just flash one slide. It is from lead selenide quantum dots coated with some molecules that had phosphorus in it, in particular topo. And then when we look at it with very low photon energy, if I look at it, this line divides any signal on this side is from phosphorus, that side happens to be from lead. And you can see when I come in with very low photon energy, I see no lead. There is one phosphorus peak, another phosphorus peak there. Now, low photon energy means low escape depth. That means I'm looking at really the topmost surface layer. And this tells me this object, lead selenide coated with topo, is covered on the surface with phosphorus-containing things. And there are two different kinds of phosphorus-containing things. I increase slightly the photon energy, and I find this peak goes down, that peak goes up. That means that is an inner phosphorus, which is attached to the nanoparticle, but this is a physisorbed on top of that. And then I see two different lead signal, one due to the surface, one due to the bulk, and that systematically changes its intensity as I systematically look deeper and deeper inside by increasing the photon energy. So you can see the kind of tremendous sensitivity that we have, which allows me to map out the elemental composition as well as ask the question, any question about the electronic structure, because photoemission is the only technique that directly tells you about the photoelectron spectroscopy. And since this particular technique also works perfectly well for planar structure, and the heterostructure that I'm going to talk about are going to be planar structure, as I have shown, you keep changing the photon energy, low photon energy, you look at the top layer, you increase the photon energy, you look inside, maybe your A is up to there, B is there, then you can go sensitively across, putting your photon energy up to there or there, and see what the changes are, and therefore see what is happening at the interface, if you're interested in the interface. And this gives you a spatial resolution which is in the perpendicular direction and not in the lateral direction by changing the photon energy. Okay, so having introduced the technique, let me get on with the main scientific topic of addressing the question of lanthanum aluminate strontium titanate. This is based on a paper that came out after much difficulty in 2016 and some unpublished result that I'll be talking about shortly. This is driven by, as always in our group, by some extraordinary students. I have always been extremely fortunate to have extraordinary students, and they passionately drive these projects. Shumanta is the person who really drove this particular lanthanum aluminate strontium titanate project. And he was very ably supported by Banabir Pal and Debraj Chaudhary. Debraj is now at Kharagpur, a faculty. Banabir has migrated to Rutgers for his postdoc. It's also supported by several people who have helped us, either with the sample, which is from Hide Takagiri's group, Jobu Matsuno, who has just shifted to Osaka University as a professor, and then from Uppsala, Olof Karis, and then these three people from two different synchrotron sources that helped us with the experiments when we went there. So this is the structure that I talked about. Lanthanum aluminate strontium titanate. This is a cross-sectional TM that I mentioned, where this part is the strontium titanate. You can see this is the strontium titanate part. And then there are 6 layers of lanthanum aluminate that has been grown on top. Now to describe to you, the strontium titanate is a high band gap insulator, and if you're not interested in the dielectric properties, it's a very boring material because it's a D0 material. It has no magnetism, no possibility of correlation effect, nothing interesting, though it's a very interesting system for dielectric purposes, and I'll come to that later, but it's a very high band gap insulator, absolutely D0 system. Lanthanum aluminate is even worse, if that is possible, because it's a higher band gap material, and of course there is no d electron, no unpaired electron, no magnetism. And you have created, by putting them together, what you have done is to create an interface. And then you ask the question, what is the property of it? And this is where you have to recall the famous line from Kromer's Nobel lecture, where he said, interface is the device which controls completely the property, because when you create this interface, the property of this material becomes that it's a high mobility metal, it shows superconductivity, it can show magnetism depending on how you grow the sample. So it's a completely qualitative difference that comes in when you put it together two materials and create an interface. And obviously then everybody was very excited. This has opened up a new field of study, and heterostructure of oxides are being pursued by literally hundreds of groups across the globe, with thousands of papers coming out all the time. Now, why does it happen? Why does it happen? There's a very simple explanation that was given in the very first paper that was from Huang's group, published in Nature, Otomo et al. Here, and they provided a very intuitive and appealing picture. What they said is, look, this is just the resistivity data to convince you that it's indeed metallic. Here's the resistance as a function of temperature. Depending on how you prepare the sample, different resistive state, but all of them are metallic. As you can see by going down to 2 Kelvin, and how the temperature coefficient is, and how it doesn't blow up and approaches a finite value as you approach t equal to 0. Okay, why does it happen? They pointed out, look, strontium titanate, though it's a very three-dimensional material, but if you think of it layer by layer and exactly with the orientation of the substrate that they have, what you have is a strontium-oxygen layer here, 1:1 composition. Strontium, we know, donates 2 electron, and oxygen, we know, accepts 2 electron. So locally, this plane is completely charge neutral, and that is indicated by that 0 on top. So strontium 2 plus oxygen 2 minus, it's a charge neutral layer. Similarly, titanium gives 4 electrons, 2 oxygen takes 4 electrons, so that's a charge neutral layer of TiO2, and that's what goes on in SrTiO3. But when you come to lanthanum aluminate, it changes. What happens is lanthanum gives 3 electrons, so lanthanum is 3 plus, oxygen takes only 2 electrons, so it's oxygen 2 minus, so you have a lanthanum 3 plus oxygen 2 minus in this layer, making it a positively charged layer. Of course, every material is charge neutral. This positive charge that it builds in this plane must be immediately compensated by the next plane, which is aluminum 3 plus and oxygen 2 together 4 minus, that becomes a negatively charged layer, which is all very fine and nice. There's no problem. So what is the implication of that? This alternating positively charged and negatively charged layers that you're creating of lanthanum aluminate on top, which appears to give such fantastic properties. Now go back to your electrostatic and think about it again. This is a more easy schematic to follow. We have this strontium titanate layer, SiO2, all are 0 charge. And then I have this charge of +1, -1, +1, -1. And what I'm plotting is charge here. In this direction is the direction perpendicular to the interface. Here is the interface. And there is a positive direction of charge, negative. So that's positive charge, positive charge, negative charge. What would be the electric field? The electric field, of course, would be like that, and the potential then, in that case, is like that. It's a dipolar field, the potential that's growing up. Now, what would be the implication of that? There is no dipolar field here, so the valence and conduction band of these will feel no potential, but as I keep going more and more number of layers, as I increase the thickness, this potential would be bending the valence and conduction band of those layers. In what way will it do that? Here is a schematic. This is strontium titanate, the valence band top, the conduction band bottom. You have a gap there which is large. This is the interface. Strontium titanate, lanthanum ends there, lanthanum aluminate begins there with an offset of the valence band and conduction band which are shown. So you have the valence band top of lanthanum aluminate here and conduction band bottom there. Now this potential that's growing up, successive layer of lanthanum aluminate, the top of the valence band is going to bend. So for a critical thickness, when you reach a critical thickness, this particular energy will cross the energy of the bottom of the conduction band. As soon as that happens, an electron from here, which is occupied, will get transferred into the conduction band of strontium titanate, which is unoccupied, and therefore this charge transfer would take place. What would be the consequence of that? It turns out that if you transfer just half an electron and make this titanium 3.5 plus instead of titanium 4 plus, so that you have now half an electron in this interface layer, charge pattern is minus half, then plus 1, minus 1, plus 1, minus 1, then this potential doesn't run away any longer. So you've stabilized that dipolar field, which otherwise was growing up catastrophically, driving this system, and that transfer of the charge now gives you a two-dimensional electron gas here. And that two-dimensional electron gas was proposed to be the driving force for all this high mobility metal and superconductivity and magnetism, etc. But what's the problem with this? There's a very elegant explanation, but happens to be that there are problems. Depending on how you make the sample, and that dependence that I'm talking about, the most important parameter is the oxygen partial pressure that you maintain in your ultra-high vacuum chamber while growing these materials by PLD, and that changes the resistivity behavior by, you can see, 7 orders of magnitude. All of them are metallic, but obviously oxygen partial pressure has very important role to play. And also, we know that the tunable carrier concentration I can measure, and that can vary by over a 5 order of magnitude. But if it was half an electron transferred per unit cell, I know exactly what the carrier concentration is. It's 3.4 into 10 to the power 14 per square centimeter. And so the polar breakdown hypothesis would record only 3 into 10 to the power 14 per square centimeter, but you have 5 orders of magnitude changes in carrier concentration. That can be 2 orders of magnitude lower than this and 3 orders of magnitude higher than this. So obviously polar catastrophe cannot be the complete answer, simply because that would require the charge carrier concentration to be exactly this. There are other issues, because obviously one thinks then oxygen deficiency must be playing a role, because strontium titanate, anybody who's worked with strontium titanate knows that it's really notorious to have oxygen defects, and oxygen defect can do many interesting and nasty things. And also there's a question of lanthanum and strontium. So strontium titanate ends, lanthanum aluminate begins. If I have slight intermixing also, then lanthanum and strontium will get mixed up, and I know lanthanum group strontium titanate is a very good metal. So that itself, this intermixing can also give rise to metallic state. Does that happen? People have tried to measure the thickness of this two-dimensional electron gas. Remember, if the polar catastrophe picture is to be right, then we have exactly one monolayer of this two-dimensional gas, one unit cell thickness. But the polar catastrophe model would presuppose that the thickness is about 0.5 nanometer. Whereas what you find from various measurements, it's actually several tens of nanometers thickness. Several tens of nanometer cannot be at the interface. Interface is 1 unit cell or 2 unit cell thick. If you have something that's 20 unit cell thick, and 10 nanometer would mean 20 unit cell thick, cannot be called a two-dimensional system or an interface phenomenon. And then one has to ask the question, then where is it? If it is not at the interface, because it's so broad compared to what an interface is, where is it? And then the nature of the conducting carrier has also turned out to be extremely surprising, because depending on how you probed it, for example, if you did DC transport and measured the mobility, you found very high mobility, but for the same sample, the carrier concentration at this value. Using the same sample, if you did optics experiment to figure out mobility and carrier concentration turned out to be much higher and the mobility much lower. As if there are two different kind of carriers in the system, one with high mobility and low carrier concentration, and another is with low mobility and high carrier concentration, which is also, of course, inconsistent with the naive picture of polar catastrophe. So there are many open issues that I have listed out here about this carrier concentration, whether the driving force is polar catastrophe alone, where is this electron gas, because the system is metallic, we know that, where it is distributed and how it is distributed and what its characters are, electronic structure is. These are the issues that we would try to address by looking through, because we have this exquisite control of looking at layer by layer the electronic structure and the composition and asking where these electrons that get doped from lanthanum aluminate come, what makes it metallic. So to start with, we have a lanthanum aluminate on top, strontium titanate below. I can get the lanthanum spectrum and the strontium spectrum. And as I know that if I increase the photon energy, I'll increase the kinetic energy, which means I'm looking increasingly deeper inside. That would tell that with the photon energy increase, lanthanum by strontium intensity will go down because I begin to see more and more strontium. And that is indeed what happens. Here is the plot of two different samples. As a function of photon energy, which increases the kinetic energy, lanthanum to strontium ratio is going down. So I have a heterostructure with lanthanum aluminate on top, strontium titanate below. But that's a very trivial statement to make because cross-sectional TM has shown it, and that's how I made my sample. Can I make a more quantitative statement? It turns out that you can. So this is the variation that I see. And I can say, okay, if I had B thickness of lanthanum aluminate layer, then what should be this intensity variation? Because I can calculate that given a thickness. So I first assume the thickness to be 2.9 nanometer, and the theoretical curve goes above my experimental data points. Then I say, okay, that means I'm overestimating. Let me assume it to be 2.6 nanometer, and then I find that it goes below the experimental data point. That means that I have an accuracy of determining what is the thickness and where the interface is with respect to the top surface with an accuracy of better than plus minus 0.15 nanometer. Of course, as professional and practitioner, I believe the error bar is even smaller, and it can be tied between 2.75 plus minus 0.05 nanometers. And that tells you the sensitivity of this particular technique, and that tells me that I have a very, very sharp interface with hardly any intermixing. So I have a very sharp interface, and lanthanum-strontium intermixing is not the cause of doping charge carriers into the system. Then I have to ask where the charge carriers are. I figured out how lanthanum and strontium is, but I know my material is metallic, so I look at those and ask the question by looking at titanium core level, because I know that when the system becomes metallic, strontium titanate, the only way it can become metallic is by doping the titanium 3D level, and locally making a titanium 4+ unit into titanium 3+ unit. And I know that the titanium 3+ signal and titanium 4+ signals are very different. As shown over here, this big peak that you see is a titanium 4+ signal, and this weak peak that you're seeing is titanium 3+ signal. These are the material samples that are non-metallic or very weakly metallic. These are more metallic, and you can immediately see, I can see where titanium 3+ is energetically. Now, if I look how this intensity changes as normalized by that one, as I keep changing my photon energy, I know exactly where titanium 3+ is. And titanium 3+ is where the electrons are, these doped electrons that make it mobile. And that is what we did by looking at the variation of the intensity, and then you have to analyze it, of course. It turns out that if I try to analyze the data with assuming one distribution of charge density that can be of any width and any concentration, charge carrier concentration, but one end of it is tied to the interface, then the best fit that I get of the experimental variation, which is this one, which tells me that I cannot have one single charge distribution tied to the interface. I then say, okay, remove that constraint, let it move and not be at the interface. And when we do that, then the best fit is this one, which also is not satisfactory, which tells me that I need a minimum of 2 different charge distributions independently optimized, and then the picture emerges that you get a very good description and a very surprising distribution of charge carriers. One charge carrier which carries 2 × 10⁻14 per square centimeter, which is the number approximately that you expect if it is a polar catastrophe model, and tied to the interface with a very narrow, about a nanometer or 2 nanometer width. What I have drawn over here, this is the lanthanum aluminate top surface, this is lanthanum aluminate, this is the interface, and that's strontium titanate. So there is one charge carrier density tied to the interface of the amount that one would recur from polar catastrophe, but there's a low density electron doped throughout the bulk, which is in the order of 0.06 electron per unit cell. And that happens to be for all samples that we looked at. Again, the same behavior. Then we asked the question, so where is this coming from? That immediately told us that strontium titanate oxygen vacancies are very common. So it must be oxygen vacancy, and we were lucky because there's a spectroscopic signal or signature of what an oxygen vacancy is. For shortage of time, I'm not going through that, but essentially tell you what the story is. The story turns out to be the oxygen vacancy also required two different kind of distributions. Now, one distribution was uniformly distributed in strontium titanate, and another was not at the interface, but at the top of the lanthanum aluminate surface. And also the concentrations are very significant. We found a 0.03, and this is an independent experiment, 0.03 oxygen vacancy. Each oxygen vacancy contributes 2 electrons, which tells you 0.03 vacancies would contribute 0.06 electron per unit cell, and that's the sort of number you find distributed throughout. So that's driven by the oxygen vacancy. What about this one? If you look at the oxygen vacancy that you get here is 0.35 vacancies per unit cell. I told you 0.5 vacancy per unit cell gives you an interface concentration of charge carrier of 3 × 10⁻14, which tells you this 0.35 would be 0.5 divided by 0.35, whatever that little correction is, which will bring you into the order of 2 × 10⁻14 per square centimeter. That means it is this oxygen vacancy that dopes them. Does that mean that there is no role of the polar catastrophe model that one talked about? Actually, we believe it does have, but it affects it in a different way. What really happens is that as you are growing the lanthanum aluminate up, and this band is bending, when now the electron you want to transfer from the topmost layer of lanthanum aluminate, it turns out the electron is coming out of the bonding level of the oxygen. And therefore, you are weakening the oxygen bond, and it prefers to go away. So the vacancy gets created, and electron gets transferred sequentially. But arising from this polar catastrophe or the polar field that grows up, bending, and then therefore stabilizing it, you have in-gap vacancy states which contribute to the electron, and those electrons provide you this interface exactly in the order of magnitude that you would expect. So given this distribution, then of course one would like to ask the question, what is the character of these electrons? Are they correlated? Because they show magnetism, they show superconductivity. Are they correlated? And so you look at the valence band study, and valence band spectra, as you can see, nice and very strong. Everybody who does spectroscopy knows that if the signal is strong, then it is not the signal you are looking for. The signal that you are actually looking for is that one. That's where the Fermi energy is. And so it's an incredibly difficult experiment, and you need incredibly brilliant and patient students to do that. And they, of course, say that because they're scared of me, but that's not true. You can see how much I smile, right? So, and they looked at it very carefully, and that part expanded is over here. You can see that there are two features, one peak here, close to the Fermi energy, another down there. Normally, we call it the coherent peak. This is the one that makes it metallic, and this is believed to be the signature of the lower Hubbard band, which makes it correlated. So we wanted to know, now if I change photon energy, and I am more sensitive to the interface states or the bulk states, do they look different? After some processing, etc., it turns out that they're absolutely identical. Here the two, one is the 3500 data, which is the dots, and 5400 data, which is the line, and they are on top of each other. Not only that, the second peak, which normally we believe to be the lower Hubbard band, turns out to be very weak, and there's no change with depth. And not only that, there's other reasons, and this paper we are in the process of submitting. This is not a signature of lower Hubbard band, but is driven by oxygen vacancy signature. Does that mean that we are always in this boring limit? Can I take just 5 more minutes? That will be 40 minutes. The conclusion here, I'll quickly rush through that. I have already told you, lanthanum and strontium, the minimal mixing across. Clearly, there are two different distributions of charges in this system. And the two-dimensional electron gas does exist with a thickness of about a nanometer or 2 nanometer, not 10 nanometer. Those measurements were averaging over part of the bulk also. It's a couple of nanometer thick. And one distribution comes from the doping into the bulk of strontium titanate vacancy. The other comes from the vacancy on the top layer driven by the polar field that grows up. And the charge carriers are very weakly correlated, if at all. Now, I'll just in 5 minutes tell you the results from this system, because this is drastically different and it contrasts what I have said so far. And this is driven by, again, another really extraordinary student, Banavir Pal, for his thesis, supported by Shamashish and Shumanto. And samples came from this group in University of Arkansas. Jack has just shifted to Rutgers, and Banavir proved himself to be so worthy that these guys told him, and now Banavir is doing a postdoc there. And of course, my partners from Petra, Uzgang Zube, and Indian Sarkar. The difference in this particular case, lanthanum titanate, strontium titanate, with what we talked about before, these are both what we call band insulator. Correlation plays no role. Because I am interested in correlation, I am making sure that correlation has to play a role by creating a Mott insulator where the insulating property comes because of electron repels each other. And repels each other by an energy scale which is larger than the bandwidth that they form. Lanthanum titanate has 1 electron in the titanium d band, and yet it is an insulator. This is a band insulator. So these are fundamentally different kind of interface that I have created. I'll not go into all those descriptions. And we get a metal, but this system has been theoretically tackled so far. And theoreticians don't agree with each other, which is a nice thing for an experimentalist like me. Because then you have to fight with only n-1 theory and not with n theoreticians. It's not very, for large n as it exists, there's not difference, but you hope that your referee is that single one. What Andy Millis and his group showed, the top layer is strontium titanate. This is the interface, and this is the lanthanum titanate. This peak is what I told you, lower Hubbard band, the incoherent peak. This is the coherent peak, and you can see a layer-resolved electronic structure. High up, your strontium titanate. This is the chemical potential, very small. In the occupied intensity, you'll have very small intensity. It's not occupied. Slowly, it moves down in, and you can see it's getting occupied, large amount of occupation, and the Mott-Hubbard feature, low Hubbard band, begins to show. That becomes intense, but it remains always at the same energy dictated by the Coulomb interaction strength. And it saturates its intensity somewhere here, but this coherent peak slowly vanishes again. So there's a lot of things happening. But somebody else said, no, that's not the case. It doesn't remain so steady. As you can see, the lower Hubbard band would move, and all the action at the chemical potential will be over in 2 layers. 1 layer there, 1 layer there. Everything else is absolutely devoid of any. So it's going to be much narrower to the electron gas if this gentleman is right compared to that gentleman being right. There are other calculations that say other things, and I'll not walk you through all the details, but there's real controversy, and this is where we came in. And we did, of course, this layer-resolved electronic structure. Besides doing the core level to figure out where the titanium electrons are, we also asked the question, what is the nature of these titanium electrons? How much of the spectroscopic signature appears in lower Hubbard band? When you do that, once again, this is the part that you are interested in. That is not the part we are interested in. We are looking at various photon energy. And then if I look at it, as you can see, even without any treatment, that there's a lot of change depending on what photon energy I use. And when we extract that and look at the behavior, this is the experimental data as a function of photon energy. You can see this is the coherent part which makes it metallic. This is the incoherent part which makes it correlated or takes it towards being an insulator, and the ratio of these two are changing. We can extract and make it quantitative how much they are changing. Straight away you can see that when I am at high photon energy, so that I am looking from strontium titanate top and looking into the lanthanum titanate, I get this intensity decreasing compared to that. That means I'm getting more correlated. As I'm looking deeper inside, this is less correlated I'm looking from top. So this being strontium titanate layer up to here, this is the interface, then lanthanum titanate. We found that the titanium 3D electrons distributed this way. This is almost 1 electron when you go deep down in, Near the interface, strontium titanate gets about a nanometer or so thick 2D electron gas, and it leaks into inside. It borrows the electrons from there and goes into that side, also on the STO side. And the spectral features, if I extract, let me point out here, yes. So it compares exceedingly with this theoretical calculation, and that's why I've shown you. This is a spectral feature extracted from our experiment. As you can see, what we can see is only 0 and below. On this side, I don't see. You can see the coherent part starts with very low, as over here, increases up to the interface layer, which is here, that is here, and then it begins to go down again as it goes down here. The lower Hubbard feature starts from here exactly like that and begins to grow in intensity and then saturates exactly the way it is here. So it is an extraordinarily, I would say, agreement between theory and experiment, in spite of the fact that the theory was proposed before, very boldly. Also, this variation of how the titanium doping takes place, that is plotted here. It is the total titanium D count, and also this line shows what is the coherent feature, or the part that makes it metallic, how it varies. In the strontium titanate end, there is no correlation effect, and so the entire weight is here. But when you get in here, which is the Mott-Hubbard insulator originally, now doped metal, strongly correlated metal, its correlation-induced feature is very high. Only this part is the coherent feature. And the corresponding calculated result, because we need to look at only that, you can see has exactly similar behavior. You have this peak and going down, this peak and going down, and the total number of electrons going up like that. So with that, let me end summarizing and contrasting to the two systems that I talked about, LOSTO, where there's very weak correlation and the electronic structure is independent of the depth, at least the gross properties. But there are two different kinds of electronic structures coming from two different effects. And here the effect of correlation increases very strongly as a function of depth, because by construction I created a band insulator, which is an uncorrelated end on top of a Mott insulator. And with that, let me end. This is just a final thing that there was also a theoretical claim that if you change the dielectric constant, then the distribution of electron density, this is the interface layer, this is the strontium lanthanum titanate side, this is the strontium titanate side, it will change very drastically. It turns out strontium titanate is a quantum paraelectric, so its dielectric constant changes very strongly as a function of temperature. And we did the experiment at two different temperatures, and they are overlapping with each other, essentially implying that the dielectric constant has no role to play in deciding how the charge density gets distributed, at least in the microscopic level as we are looking at right now. And let me thank you for your patience.